All right, today is 9.6 day 2, and we're going to continue our conversation about polar coordinates. We talked in the previous lesson about how to convert coordinates so far. Now we're going to talk today about how to convert equations from polar to rectangular. So there are only three things that you can use when you're converting equations, and they're all the same things from yesterday. We can use that x is equal to r cosine theta. We can use that y is equal to r sine theta. And we can use that x squared plus y squared equals r squared. That's it. If you're not using one of those three things, you're probably doing the problem incorrectly. So the first one says convert the rectangular equations to polar. Right now they say rectangular. So that means we have to get rid of this x and replace it with r and theta. Rectangular means x and y. Polar means, r and theta. So you have to completely get rid of these and turn them into these. So just looking up there, what does x equal? X is r cosine theta. So x, dang it. Let me white out. X is r cosine theta. Awesome. Usually, just like when we are writing rectangular coordinates, we like it to be y equals something. When we're writing polar equations, we like it to be r equals something. So we're going to get rid of this cosine. We're going to divide it. And anytime cosine is in the denominator, it turns into secant. So you could write 4 over cosine theta. That's okay. But the big leagues, we want to write 4 secant theta. Next, I've got y equals x squared. So I've got a couple of different things we're going to do here. Looking up above, we know that y is r sine theta. So I'm going to start with that. We also know that x is r cosine theta, and that is squared. So I literally am just substituting in for those letters. So r sine theta, that's working for me. Squared just means this guy twice. That means there will be 2 r's and there will be 2 cosines. So I kind of want to get my cosines on one side, or I should say my trig functions anyway. And we need to get our r's on one side. So everybody's got to kind of flip-flop. Usually students like to move the smaller letter over. So we're going to move this 1 r over. And the way that you're going to do that is by dividing. It's being multiplied right now to that sign, so we have to divide it off. So we've got a sine theta equals, and one of those r's is going to cancel, but one will still be left there. So in order to solve for r, we're going to divide by cosine squared. And so r is going to be, right now we have sine over cosine squared, which is legitimate. Sine and cosine, with a sine on top and a cosine on the bottom, and another cosine on the bottom, we can kind of rewrite this a little bit more. We could write this as tan with a secant. That would be the ultimate answer. I would take this sine over cosine squared. That's not illegal. This is kind of the prettied up version. A couple more to convert. These ones are going the other way. So now these are in polar and we need to go to rectangular. So this first says r equals 2. And looking up at these equations, I have an r there, but it's kind of tied up with some stuff. I have an r here doing the same thing. This one actually has r by itself, but I need it to be an r squared. So I'm going to square both sides, which I can do. It's kind of like multiplying both sides by 2 or dividing both sides by an r. As long as you do both sides, you're okay. So now I've got r squared equals 4, and I know what r squared is equal to. That's equal to x squared plus y squared. So I'm going to substitute that and make it x squared plus y squared equals 4. Which is just the equation for a circle. So that's pretty awesome. Next one says r equals secant theta, and it's kind of going to be the reverse of this guy. So first I'm going to change that secant into 1 over cosine. We don't have a secant up here, so I want to put it back into its original trig function. So making that 1 over cosine, I'm going to multiply both sides by cosine. So right now I've got cosine theta times r equals 1. And anytime I have an r and a cosine together, that's x. So r cosine theta or cosine theta times r, that's an x. So x equals 1. One more to go. And this is the most different kind because we haven't done one like this yet. It's got a theta equals pi over 3. Now up here, I do have thetas, but they're tied to their trig function. You can't just separate them, so it's not going to work. So what we do to both of these, the only thing we haven't really used yet is being able to tangent both sides, which sounds kind of weird. But if I tangent theta and I tangent pi over 3, tangent of theta was one of our other little equations to use, y equals x. I should add it here. The only time you'll ever use it is when we have ones like this, when you have like a theta equals an angle. And so I know that tangent was equal to y over x, and the tangent at pi over 3, I would just have to go look on my circle, and that would be square root of 3 over 3. And so now doing a little solving, like I said, we like it when it's y equals, we don't want the x over here, so we're going to multiply both sides by x. And so I end up with y equals square root of 3 over 3 x. This is literally like slope. You have a slope of square root of 3 over 3. Go like this. Change that to a 6, because I just realized that I did the value for a pi over 6, not a pi over 3. Instead of changing all these ones, just change that to a 6 so that it matches. I just took the wrong tangent value. I wasn't really looking that closely. So, converting equations. You've got 4 to use. This guy's used the least. Only happens when we've got theta equals some kind of angle. Most of the time you're just looking for, hey, what is x? And then substituting. Remember, when you have a polar one, you want to solve for r and get r by itself. And when you have rectangular, you need to make sure that you only have x's and y's in the end.